and especially Zinovi. In some sense, Zinovi's to blame for this. So I got into this problem from two directions. One, Skip Garibaldi, and I started working on rings of invariance for algebraic groups acting on linear spaces. And then Zinovi had asked some questions about essential dimension for spin groups. And so that got me started thinking about some of these things. So anyway, I'm just going to give an overview of some results. It's not going to be all that technical. I'm going to avoid the details. If you can look at some of the papers if you're interested. So anyway, so the general problem is the following. Okay, what? So we have some algebraically closed field of characteristic P, which could be 0 as well. I have an algebraic group over that field, which will be almost always a simple algebraic group. And I have some, and it's acting on some irreducible variety, which pretty much will be, for the most part, will be some linear space with a linear action. Okay, so we'll say that a property is generic if it holds for some non-empty open subset of X. So for example, if you look at the minimum dimension of the stabilizer of some point in X, that's constant on some open, non-empty open subset. And so that's an example of a generic property. So what I'm interested in is the stabilizer up to the constant class of the stabilizer, is that a generic property? So is there an open subset of the variety so that the stabilizer of a point on that open subset is unique up to conjugacy? And so in characteristic 0, there's a very general result. It was originally proved by Richardson. So if you're in characteristic 0 and you have a smooth affine variety and you have a reductive group, then there is a generic stabilizer. That is, there is a subgroup H of G and a non-empty open subset so that all the stabilizers of points are conjugate to H. And it's an old paper, I think, from the 70s in the annals, and fairly short, actually. Okay, so it holds in complete generality. However, it fails if you drop most of these hypotheses. So it fails in positive characteristic. It fails if it's not reductive, even in characteristic 0 and so forth. But as I said, I'm mostly going to focus on linear actions. And so it fails in positive characteristic, even for a semi-simple group acting on an irreducible module. Although up to this point, we have exactly one example where this fails. So which I'll mention a little bit later. So, okay, so in positive characteristic, you're not going to be able to prove it the same way. Right. So as I said, I'm going to consider basically simple groups acting irreducibly. So in characteristic 0, this was well studied starting many years ago. Popov, A. Popov, and Elvashali, and quite a lot of others studied this problem. And they classified all generic stabilizers when G is simple and V is irreducible, an irreducible module. So linear space, and other cases as well, projective spaces, products of projective spaces, and various other things. And there's a really nice article by Vinberg and Popov in the Encyclopedia of Mathematics that gives the history, the context, and all of the results. Lots of nice tables and so forth, and related results about invariance and so forth. So here's a sample result in characteristic 0. Suppose G is a simple Lie group, and V is an irreducible finite dimensional rational module. So if the dimension is bigger than the dimension of G, then generic stabilizers are always finite. And as by Richardson, we know they exist, but they're always finite. Actually, if you know it's finite in characteristic 0, it's not hard to prove it's generic, because there's only finitely many conjugate. If the generic stabilizer is finite, you can show that there's an open subset where the size of the subgroup is constant, and there's only finitely many conjugate classes of subgroups order n in characteristic 0. That's not true in positive characteristic. So it'll be a generic stabilizer. And moreover, there's always a regular orbit. So that means there's always some point where the generic stabilizer, where the stabilizer is actually trivial. Okay, there's actually an interesting story about that in one of the appendices to Mumford's book on varieties, one of the later versions. They give a list of 5 or 6 equivalent conditions for a group to have, and 2 of them are in particular that there's no regular orbit and the ring of invariance is a polynomial ring, and under these hypotheses. And the proof is you look at the 2 lists. I mean, that's the proof. It's not that you show one property implies the other. But it turns out that that's not right, because what they really meant is it's equivalent, that the generic stabilizer is non-trivial, is equivalent to the ring of invariance being a polynomial ring. And but when the generic stabilizer is finite but non-trivial, it's still a polynomial ring. But in fact, there's always a regular orbit in characteristic 0. I think V. Popov, Vladimir Popov, was maybe the first one to notice this mistake, and point out that there can be regular orbits and it'd still be a polynomial ring. Okay. So, oh, come on. All right, so in characteristic 0, you have a lot more tools, of course. You have the file dimension formula, you have the character formula, you have complete reducibility for subgroups, reductive subgroups. In positive characteristic, we don't even know the dimensions of the irreducibles in general. So we're going to need to use different methods. We don't know that generic stabilizers exist even to start with. So fortunately, we do know by Permat that except in characteristic 2 and one example for G2 in characteristic 3, any weight that occurs in the Weil module still occurs in the irreducible and positive characteristic. So it, first of all, gives you a lower bound for the dimension, and still says you can still look at weights and to help in this. So, and there's a very nice article by Lubeck where he gives lower bounds for dimensions of modules in positive characteristic. He sort of has a general result for a large rank, and for small rank, he just gives a list of all modules of small, not all that small dimension, but anyway. The other thing is in characteristic 0, in positive characteristic, you really want to think of the generic stabilizer as a scheme, as a group scheme. So you have to worry about not only the points, but the Lie algebra stabilizer as well, and moreover, more generally as a scheme, because just knowing the points in the Lie algebra doesn't always tell you what the group scheme is. I tend not to think of group schemes as if I don't have to, but of course that means, for example, when I'm talking to Eric Friedlander, we don't speak the same language, and he says, what the hell are you talking about? Points? What are those things? I mean, so, but so I think he'll probably be happy that I'm mentioning schemes here. So, and there's a reason for worrying about it as a scheme, which will come up a little bit later. Okay, so as I said, so just knowing the stabilizer and the Lie algebra is not enough to know the group scheme in general. But there is one case where, in fact, it is. If the generic stabilizer happens to be, if a group scheme is smooth, then it is sufficient to know the points, because then the Lie algebra is just the Lie algebra of the points. So in particular, if the dimension of the points is the same as the dimension of the Lie algebra, then it's smooth, and then you know the group scheme. Okay, so if we're in those cases where we just can do them problems essentially separately, and then we know the stabilizer is a group scheme. Okay, so most of the time it is smooth, but there certainly are cases when it's not smooth, and so you need, in those cases, you need to do some extra work, not just to, the group, the points, the Lie algebra, but you still don't know the group scheme. So in fact, there are some interesting, so I should mention before, this is joint work with two sets of papers, one with Ross Lawther, who's at Cambridge, and the other with Skip Garibaldi. This has been an ongoing long project with both of them. It's been going on for many, many years, but okay. So, and in fact, this can happen even in good characteristic. For example, the smallest example I think where this works is if you take B2 on the module omega-1 plus L omega-1 plus omega-2 in characteristic 5, the generic stabilizer is mu5. So there are no points, but the Lie algebra is one-dimensional. What happens in any other characteristic, even including characteristic 2, the generic stabilizer is trivial for B2 for that module. But the problem is in characteristic 5, that module drops from dimension 16 to dimension 12. So you pick up, you have a generic stabilizer, at least for the Lie algebra, non-trivial one. And in fact, it happened. There are examples for any characteristic, although not very many. For large character in good characteristic. So, but in particular, for any P, you can take SL4 and you take the module L of Q omega-1 plus omega-2. So it's a tensor product of a twisted natural module tensor the orthogonal module for SL4, which is is isogenous to SO6. So it's got dimension 24. And the generic stabilizer has no points, but is a one-dimensional, but the Lie algebra again is one-dimensional, which can be seen easily because for the Lie algebra, the module is just basically 4 copies of the orthogonal module because of the Q there, the Lie algebra X trivial on that part. Okay. All right, so what happens in characteristics are positive characteristic in general. So what's the analogous result for, so mainly I'll focus when the dimension is big of the module compared to the group. Of course, the dimension is smaller than the group, then of course the generic stabilizer cannot be trivial. But there aren't very many modules where that happens. All of them, they're relatively easy to work out, at least the dimensions of the stabilizers and so forth. So I'll mostly focus in an interesting case where the dimension of the group happens to be equal to the dimension of the module. Of course, conceivably, the generic stabilizer could be trivial or finite, but it never is. In fact, the only module where we have equality, it turns out to be the adjoint module. And in that case, the generic stabilizer is generic. In almost all cases, is just the maximal torus. Sometimes, especially in characteristic 2, there can be a 2 on top or something small on top, so it's not connected. But okay. So with Lawther, we first of all proved that just as groups, just as the points, there is a generic stabilizer, and we actually classify all of them. And with Skip, we compute the Lie algebra stabilizer and show there's a generic stabilizer, and compute what it is in all cases. There was some earlier work in the Lie algebra case by two of Permet's students computing that, showing that for very large modules, which includes most of them, a lot of them anyway, the generic Lie algebra stabilizer is 0. And maybe I'll say just a little bit. So there's advantages both ways. Of course, Lie algebra, especially in bad characteristic, can be a royal pain. On the other hand, they're algebras, so you can use a lot. You can use just some linear algebra. So, for example, to show that the Lie algebra stabilizer is 0, if you find one point where the Lie algebra stabilizer is 0, you know that's a generic property. That's the minimum dimension, and so it holds on an open subroid. And so, especially in bad characteristic, for a fairly small module, you can just compute in magma or gap, pick a random point, compute its stabilizer. If it's 0, you're done.
I have a question.
What?
I have a question.
Sure.
When you talk about Lie algebra, do you use P Lie algebra or Lie algebras?
Well, we're taking the Lie algebra of the simple algebraic group, so it's got the P structure is included. So it's a restricted. It's got the P power action on it.
Yeah, yes, but you work in that setting. I mean, with this.
Well, we just worry about. We use that sometimes, but we really are thinking of it just as the Lie algebra.
Okay, thanks.
But we use the P power map does come up, for example, in some of the examples, which I'll show later on. Okay, as I said, with Ross, we computed for the points, and for Skip, we computed for the Lie algebra. And there are a few cases where, as I said, we just put it on the computer, or we, meaning Skip, puts it on the computer and picks a random point. And as I said, when it's 0, you're done. And even if it's not 0, we have some condition, especially if it turns out to be just a toral subalgebra under a suitable condition, you can prove that then it's generically that. So, all right. Okay, so here's the result for if the dimension is bigger than the dimension G, and V is faithful. I'm going to assume faithful and irreducible. If it's not faithful, you can mine out by the kernel and essentially reduce to that case. Although when you have some special isogenies, of course, the kernel can be pretty big in bad characteristics. So, or if it's a Frobenius twist, then the Frobenius kernel can, there is a kernel. So, but pretty much one can reduce the faithful case. Okay, so the generic stabilizer is always a finite group scheme. Not a finite group, but it's always a finite group scheme. And in fact, usually it's finite in tau. But again, I gave you some examples where that's not true. And again, usually but not always, there's a regular orbit, even for the points. But there are examples where there's a regular orbit for the points, but not for the group scheme. Meaning the generic stabilizer has no points, but the Lie algebra is non-trivial. Usually, but not always, the generic stabilizer is smooth. So most cases it is. And of course, when it is smooth, we know what it is because we know the points, we know the Lie algebra, and so we know what it is as a group scheme. And almost always, it's a commutative group scheme. And in fact, the connected part is always commutative in the sense that the Lie algebra of the generic stabilizer is always contained in the Lie algebra of a maximal torus. Of course, this isn't true if the dimension is small, but if the dimension is larger than the dimension of the group, you have that. Now, all of this sort of comes out from the classification. I don't see a way of proving these things. Again, because it's usually, but not always, seems you're not going to be able to give a proof without sort of knowing what the stabilizers are. Of course, if the dimension is less, is less than or equal to the dimension G, then the generic stabilizer will certainly not be trivial. Well, as I said, you have to worry about the case where dimensions equal, but the only module that occurs there is the adjoint module. And it's always smooth in this case, except for G equals G2 and characteristic 2, where you have the 6-dimensional module, which normally is 7, but it drops in characteristic 2 to 6. And in that case, you have the points, and it turns out the Lie algebra has dimension 1 and larger. So there's sort of a copy of the alpha A in group scheme notation. It's sort of on top of the smooth part. Okay, so rather than really, I'll mention a little bit about the proof if I have time at the end, but let me give some examples, which I think are, there's some interesting examples that come up. So one example is that if you take SLN and you take V to be one of these two modules, so it's a tensor product of a Frobenius twist of the natural module, tensor either the natural module or the dual of the natural module. And it's easy to see by Lang-Steinberg that there's a dense orbit on projective space, or if you replace G by G, let GLN act, there's a dense orbit. In fact, you can identify this module with n by n matrices, where you have sort of in the second case, you have a twisted conjugation action. So you're conjugating by U so you multiply by U on the left and U to the minus sigma, where sigma is the Frobenius on the right. And in the first case, it's sort of twisted bilinear forms. Anyway, so there's a dense orbit. So certainly there's a generic stabilizer, and it's not very hard to see that, in fact, it's finite étal. And in the first case, it's the special unitary group over FQ. And in the second case, it's an SLNQ. There's finitely many orbits on projective space. In fact, there's a dense orbits, which is a necessary condition, but there's only finitely many. And this really depends on some results about representations of quivers or some sort of representation theory. The second case is actually quite easy. You're just classifying n-dimensional modules over the twisted polynomial ring, where you're twisting by Frobenius. And that's a non-commutative PID, and it goes back to, I think, Jacobson described all the modules. And you have a Kroll-Schmidt theorem, so you just have to look at the indecomposables, and they're quite easy to list. In the first case, it turns out, as you're looking at twisted bilinear forms, and Riem looked at this problem in much more generality for the invertible, the non-degenerate case. But in the degenerate case, it basically goes back to Kronecker, and it goes back to his theory, his theory of pencils. And in Riem's paper, Gabriel has an appendix where he points this out. So you can just write down what the indecomposables are, and then you know what's going on. And it turns out also there is no regular orbit in this case. So this is shows that what happened to characteristic fails in positive characteristic. And it turns out there actually is one more orbit besides this dense orbit. There's one orbit where the stabilizer is finite for SLN on points, but it's non-trivial. So there is no regular orbit. Okay, so here's another family of examples. So this goes back to Winberg's theory of theta actions, and I'm just going to give a special case of it. So assume the characteristic is not 2 for this, and you have an automorphism of order 2 of the algebraic group. So it acts on the Lie algebra as well. And then you can decompose the Lie algebra as the fixed points of theta plus the -1 eigenspace of theta. And so then the L1 is a module for the centralizer of theta. And in characteristic 0, I said Brooke studied this in much more generality. And let's take the special case where theta inverts a maximal torus. So it could be an inner automorphism, it could be an outer automorphism as well. And let's look at that case. So here's the first example. Take G to be SLN, then H is just SON, and L1 is the symmetric square of the natural module. Take G to be E8, then H is the half spin group of rank 8 as half spin 16, and L1 is the half spin module of dimension 128. Where G is E7, then H is SL8 mod mu4, and L1 is wedge 4 of the natural module. There's another example with the 8. If you take an order 3 automorphism, where you end up with SL9 acting, and there's 2 pieces then, and you're looking on wedge 3 of the 9-dimensional module. Okay, so theta inverts a maximal torus, which means that it's acting, if you take the Lie algebra of that maximal torus, it's acting by -1. So that carton lives is contained in L1. So in particular, L1 contains regular semisimple elements. That's an open condition. So almost all the elements in L1 are regular semisimple in the Lie algebra of the algebraic group. And it particularly follows from this that if you take a generic element in L1, then the stabilizer, well, you can conjugate it so it's living in T is going to be, so it's going to be the intersection of this maximal torus, which will be the centralizer of that semisimple regular element, intersect H. And so H is the centralizer of theta. Theta is acting on -1. So what's that going to be? It's going to be the 2 torsion subgroup of this maximal torus. So it'll be Z2 to the 8. Z2, some elementary abelian 2 group will be the generic stabilizer. And on the other hand, because it's acting as -1 on that carton, the Lie algebra stabilizer is 0. So this is finite étale elementary abelian 2 group. It also, you can show that this L1 contains a regular nilpotent element. Ross and I just write down what this element is. And theta acts, it turns out you can show that theta acts by inversion on the centralizer of this, the regular unipotent element, and therefore also on this acts by -1 on the centralizer of the regular nilpotent element in good characteristic. Because in good characteristic, the centralizer of the nilpotent element is the Lie algebra of the centralizer of the regular unipotent element. And so there is a regular orbit as a group scheme. Okay. Okay, and that can fail in bad characteristic because the centralizer of the nilpotent element can be much bigger in the Lie algebra than just the Lie algebra of the unipotent element. Okay. In character, you can still go through this in characteristic 2. You still have the group. You have a Z2 gradient on the Lie algebra in these cases, and you still have this module, but you do not have regular semisimple elements anymore in the non-trivial piece, and using the power map, the 2 power map, for example, it's not hard to see that the generic stabilizer for the Lie algebra is non-zero. And I'll just mention it. But it turns out the points are always still finite in these cases. And if G is E8 and you take H to be the half spin group and the module, a half spin module, then the generic stabilizer in all characteristics is Z mod 2 to the 4th cross mu 2 to the 4th. And as Permet showed us in characteristic 2. All right. And okay, so going back to that half spin group in particular, and spin groups more generally, if you have a generically free versal action, and if you want to ask about what a versal action, ask Zinovi. But linear actions are always versal, so faithful linear actions. So you can get upper bounds on essential dimension from this. So you can show if you have the spin group for an odd at least 15, then G is generically free on the spin representation. If it's a half spin for n bigger than or equal to 18, it's generically free. And if you have a half, as I said, for a half spin 16, you get this. But so from that, it's easy to see it acts generically freely on the direct sum of the half spin module and the orthogonal module. The full spin group acts generically freely. And this gives upper bounds, as I said, for the essential dimension, because if you have a generically free versatile action, you get this upper bound dimension V minus dimension G. And well, it turns out, fortunately, I mean, usually when you use this method to get upper bounds, they're not anywhere near the right answer. But fortunately, in this case, various authors had computed lower bounds for these groups, and it turns out they're equal to the upper bounds. So you get the exact formula for the essential dimension of these groups. So there was a paper of Bronson and Zinovi and Vistoli, and then Shiraznov and Merkurov, and then in characteristic 2, Bert Totaro computed the lower bounds, and they're all the same. So in the first paper, they did it in characteristic 0 because, and they got the exact answer. I mean, they computed the lower bound in all cases, but in characteristic 0, because of the results on generic stabilizers, they got the exact answer. And then Skip and I gave the upper bound for the spin groups and half spin groups, and so we got the answer. But they hadn't proved the lower bound in characteristic 2, so that was still open, and Bert did that more recently. So a nice observation here is that the essential dimension of from this it follows that spin groups and half spin groups have very large essential dimension. It's exponential in the rank because the spin module is exponential in the rank. And but for any other form of a simple algebraic group, the essential dimension is at most it's quadratic in the rank. You have this formula that was proved by various people, lots of different people. Skip and I gave a fairly short proof of this in all characteristics. For PGL2, that formula doesn't quite hold. The essential dimension's 2 in that case. Okay. All right, so here's another interesting case where one wants to look at generic stabilizers, and in particular, so take a homogeneous space and take a direct product of homogeneous spaces. If you could also vary the H there. So instead of taking G mod H cross itself, you could take G mod H cross G mod K. And of course, this is related to the other problem, especially when you have large generic stabilizers for linear actions. If you want to see what happens on V1 plus V2, of course, the generic stabilizer is just going to be the intersection of generic stabilizers, assuming it exists. So this was, what's the smallest P you need for the generic stabilizer to be, say, trivial or finite? What's the smallest B so that you have a regular orbit, which is closely related to that, but not exactly the same. And as I said, is there a generic intersection? And of course, if H is reductive, then there is by Richardson's theorem, and characteristic 0, then there is by Richardson's theorem. There is a generic intersection, because then that's a direct product of smooth affine spaces. And I'll just say that this was a paper I wrote with Tim Burness and Jan Saxel, and we show that most cases for B equals 2, the H intersect HG is trivial for generic G. And in almost all cases for H maximal closed subgroup, we compute the exact value of B to get down to trivial or to finite. And this is a classical problem for finite groups. You have a permutation action and you're asking for a base size. You want to take a collection of elements in this permutation representation so that the stabilizer of that set of points, that is, preserve the points, not the set, the point, each point is you want to find the smallest set that has that property. So that's called the base size. And the algebraic group results actually give results for finite groups, as it turns out. So for example, if you go back to the Windberg example, where theta is that involution, then you can see it follows essentially from the same argument they gave, that the generic intersection of two conjugates of H is the two torsion in a maximal torus. And so it's trivial and characteristic too. So even in characteristic two, if you take the automorphism that inverts the maximal torus, this is okay. And so generically the intersection is trivial, but in characteristic not two, it's again, it's an elementary abelian two group. And you can also show that any element of G is a product of two conjugates of theta. And so a special case of that result is that over an algebraically closed field or wherever, just closed under square roots, any matrix, any square matrix is similar to a symmetric matrix. So it's a generalization of that fact. In particular, it inverts a regular unipotent element. You can prove that, you have to prove that. And then it acts as inversion on the centralizer. And so you can find a G so that the intersection is trivial in all these cases. So the generic intersection is finite but not trivial, but it can be. And in fact, that G is essentially unique. There's essentially one orbit for that, one regular orbit. Okay, so as I said, one of the reasons I got into this was with Skip was looking at rings of invariance. So here's a result that Skip and I had proved back in, I think, 2015. And now using these results on generic stabilizers, you can give a much quicker proof. So it says, suppose you have a simple algebraic group, you have an overgroup of H. So H is supposed to also act on V. So H acts on V, so it's contained in GLV. And assume H is connected. So if the dimension of the ring of invariance is the same, then in fact, the ring of invariance are equal. And moreover, this happens only if the ring of invariance is at most one dimensional, or as characteristic two, G is SON and H is SPN, and V is essentially wedge two of the natural modules, the irreducible part of that. So,
no, sorry, I do not understand the statement. G act on V, but
H acts on V as well. So I left out the hypothesis. H is contained in GLV. So there's
okay. Okay. Sorry.
Yeah, so H is acting on V. Otherwise, it doesn't make sense, as you say. Right. And so what this says is that most of the time, if you take an invariant, so if you have this situation and you take a G invariant, then in fact, G is the connected component of the stabilizer of that. So a special case of this is like for E8, if you take the degree 8 invariant for E8 acting on its adjoint module, then in fact, E8 is the stabilizer of that, which apparently was an old question. On the other hand, that can be proved much simpler. You don't need all of this machinery because in fact, E8 is a maximal closed subgroup of SO. There's nothing between E8 and SO, which is an easy fact of about representations of algebraic groups. So, but in fact, that's sort of how Skip and I started, by looking at that. And okay. All right, so let me talk about the proof of the generic stabilizer result for a bit. So I'll say the proof with Ross uses sort of an analysis of root strings. And again, using Permet's result that we still know we have the same weights occurring, we just don't know what the multiplicities are. And in fact, we show that the generic stabilizer for one is in fact implies this condition, that the dimension of the fixed points for any element plus the dimension of the conjugacy class of that element is strictly less than the dimension of E. And that's an easy result. If you have this inequality for all X, or in fact, just for all X of prime order, in fact, even less than that, but that implies the generic stabilizer for points is trivial. And similarly for the Lie algebra, if you have this inequality for the Lie algebra, it says this. And in fact, using this root string analysis, you get even more. That it's not for assuming the dimension of V is bigger than the dimension of G, except for a few small cases, you actually have this inequality. The dimension of the fixed points is less than the dimension of G minus the rank of G. As I said, most of the work goes into analyzing the smaller cases. And we
Sorry,
also,
Bob, what are you proving now? Which theorem?
this is proving the generic state, classifying the generic stabilizers. So if you have this condition, this inequality for all X, or for all, you don't need to check it for all X, but both for the group and for the Lie algebra, then the generic stabilizer is trivial. So this is an old observation. I don't know who first made it, but it's enough to prove this, to get the generic stabilizers trivial. And so we prove that. That's what Ross and I prove for the groups, and Skip and I prove in most cases for the Lie algebra. But in the group case, it turns out it's if and only if. For the Lie algebra, that's not true. So if the inequality holds, the Lie algebra stabilizer generically is zero. But it can be zero even if the inequality fails. And with Ross, we also look at actions on Grassmannians. And in fact, there's exactly one case, so with a Grassmannian where there is not a generic stabilizer. So if you look at B3, acting on the spin representation of dimension 8 and characteristic 2, if you look at the 4-dimensional Grassmannian, the generic stabilizer is an A1, but there's in fact a 1-parameter family of stabilizers. So they're all isomorphic, but they're not conjugate in characteristic 2. And this tells you that in fact B3 cross SL4 acting on V tensor, the natural module for SL4, does not have a generic stabilizer. You can translate Grassmannian actions to these tensor products. So this is the only example we know where there is not a generic stabilizer. So maybe it's true in characteristic not true in a much more general setting. I don't know. Ben Martin has some general results, but again, certainly Richardson's theorem is not true, so you have to be careful. So for Lie algebras, we have a much different proof. So here the idea is we don't really want to look at the actions. So here we just prove a generation result for the Lie algebra. So if you have say a classical Lie algebra to start with, and you take the dimension of the largest eigenspace of an element in the Lie algebra on the natural module, then it can generally be generated by n over e conjugates of that element in the Lie algebra. And from that trivially gives a dimension of the fixed points is at most d minus 1 over d times the dimension of v. So it gives you this bound on the fixed points. Of course, you have a bound on the dimension of the constant class. It's at most the dimension of g minus the rank. And so you can show that means that you have this inequality holding in most cases. And in fact, you can prove that it's sort of roughly, as long as the module is at least dimension 2r squared, and you don't even need semisimple for, you don't even need irreducible. You just sort of need that the Lie algebra has no 0 points. It doesn't fix anything. It has no trivial submodule. And for exceptional Lie algebras, 5 conjugates suffice. And 4 for G2, except in very bad characteristic. And this was proved by R.E.A. Cohen and Steinhaus and David Wales for long root elements in characteristic not 2, or in I guess maybe characteristic not, in good characteristic at least, for Lie algebras, for these exceptional Lie algebras. Okay, actually, R.E.A. was giving a talk at Oberwolfag and asked this question. And of course, nobody, if you didn't think about it, you wouldn't know 5. Who would guess 5 for E8? for example. So he was giving a talk and he said, okay, how many conjugates do you think generate? And so I said 5. And he looked at me sort of with an unhappy look and said, how about E7? I said 5. He said, how about E6? 5. Well, the thing is, I had talked to Permet just before the talk and he had told me the answer. So, but Arye wasn't happy. So, and for algebraic groups, one can look at this problem as well. For finite groups, Jan, Sackler, and I gave upper bounds for any element in a finite simple group. How many conjugates do you need? We didn't have quite a strong result. We just gave an upper bound, which is for characteristic for the classical groups is essentially the dimension of the natural module, or n+1 in some cases. And for the exceptional groups, we gave a worse upper bound. In recent work with Tim Burness and Spencer Gerhard, we proved that for the algebraic group, 5 conjugates, for example, of any element in E8 will generate E8. Topologically, of course, you have to be working over a field that's not algebraic over a finite field. Otherwise, it's group's locally finite. I should mention the work with Jan had nice consequences. It classified irreducible modules for finite groups in which you had a very large eigenspace. And in particular, it classified bireflection modules. That is, modules where you have an element that fixes a codimension 2 space. And for dimension bigger than 10, you just get the obvious things, the same as characteristic 0. So, all right. And in fact, using that result, you can prove that 5 works for E8 of Q as well, except for possibly 5 finitely many Q. I'm sure there are no counterexamples, but the proof only shows this. All right. Okay. So maybe I should say a word about so the thing is, we don't exhibit for the Lie algebra, at least in small cases, especially for the exceptional cases. One way of proving this is just, say for long root elements at least, is write down the Lie algebra, take 5 random long root elements, and they're going to generate E8. So you write down E8 and small characteristic at least. And you can sort of do this over Z even, so which shows that it works in almost all characteristics, and then just, if you have to, check some of the smaller ones. But for classical groups, it's not so easy to actually write down, even though almost anything you write down will work. So what you do is you prove that you can inductively, you can find the right number of conjugates that generate different very large subgroups, and you show that either at so you find some that generate something that acts irreducibly on some very large composition factor, and then you find some that act in sort of an incompatible way, but those are closed condition. If the first condition held generically, then you couldn't have the second condition holding. So you exhibit things that sort of say it can't be this generically and it can't be this generically. So the only thing sort of it can be generically is the whole thing. I mean, I'm leaving out a lot of details, obviously, but so you actually don't just write them down. Although I should say for Steinberg proved that the finite simple groups of Lie type are 2 generated by, he actually wrote down 2 elements. And Aschbacher and I proved that all the finite simple groups can be generated by 2 elements, but Steinberg did about 99.9% of the work. But and when I give the talk, when I mention this, I say, well, Steinberg was a hell of a lot smarter than I was. So, okay. I should say one thing to note is that in characteristic 0, if to generate a simple algebraic group is actually an open condition. So if you look at, say, pairs of elements in the simple algebraic group which generate, that's actually a Zariski open non-empty open subset. And that's not very, I don't know who first observed it. I wrote it down at some point. People in the characteristic zero case did analogous kinds of things, but mostly in the Euclidean topology, not the Zariski topology. In positive characteristic, it's not true, because in fact, if you take the points over FQ or FQ bar, you always generate a finite group. So there's a dense set of points where you're always generating a finite group. But it turns out it's still generic, meaning it's the complement to a countable union of proper closed subsets. Okay, as I said, here was the idea of the proof, but which I mentioned. Here's another result that was joint work with Briard, Ben Green, and Terry Tao. If you take two non-commuting words in a free group on two generators, and you pick random elements in the group and insert them into these two words, then then they will generically generate a Zariski dense subgroup. Okay, since there's only countably many pairs of words, you can take the union of all of these things, subsets, and it's still, or the intersection of all of these things, and it's still a generic subset. So you get that the set of pairs that generate a strongly dense subgroup is generic. Strongly dense meaning any non-abelian subgroup is Zariski dense. And this had examples, this came up with looking at Cayley graphs of finite groups if we type. Was the motivation for that. All right. So I wanted to close this with a question that I've been asking for years and still have not gotten an answer for. So hopefully somebody in the audience can figure this out. So in this paper with Liebeck and McPherson and Seitz, we actually classified the maximal subgroups of SL. So on where you have finitely many orbits on a module or on the Grassmannian. Or on Grassmannians of this thing. And of course, in characteristic zero, this is a classical problem. But one thing we ended up proving here, G is just any closed subgroup. It doesn't have to be reductive. It doesn't have to be simple. If you have a closed subgroup of GLV and it has finitely many orbits on a d-dimensional on d-dimensional spaces, left out spaces. So on the Grassmannian, and d is at most half the dimension, then it has finitely many orbits on d-1 dimensional orbits as well. The proof of this is you reduce to finite, you look at finite groups. So we first did it in positive characteristics. So you look at the finite groups, and so you have a subgroup of GLNQ over a finite field. And there you can actually show, just using very elementary character theory, that the number of orbits on d-1 spaces is actually at most the number of orbits on d spaces, just by looking at permutation characters of the various parabolics in GLN. And then using sort of descent theory and Lang-Steinberg, that implies that if you have only finitely many orbits on d spaces, you have only finitely many orbits on d-1 spaces. It doesn't give you an inequality though, because stabilizers are disconnected. And so the number of orbits over the finite field is not the same as the number of orbits over the algebraic group. So it can decrease. And so we still don't know. Does the inequality hold for algebraic groups? It does for simple algebraic groups acting irreducibly, because there's almost never finitely many orbits. And you can look at the cases where it is. The main case is when G is a symplectic group or orthogonal group. And then you can see that in fact it does hold. And okay, and so secondly, find a characteristic zero proof of this. The way we prove it in characteristic zero is by saying, well, it holds in positive characteristic, and then sort of as using a compactness argument, you can prove it in characteristic 0. I mean, you have to be actually have to be a little bit careful to do this. And McPherson is an expert in this, so he did this. But so it holds in characteristic 0. But there should be just, I mean, it should be easier in characteristic 0. And so far, I've asked various people: Nolan Wallach, Costant, Roger Howe, and so either they weren't interested or didn't find something. But I think the first probably. But so anyway, and this is as I said, this is related. This GLMS paper was the same paper where we looked at that example, that twisted tensor product action, where you got some things. And Gary Seitz was not actually very happy that I was using quivers in representation theory to prove these results about orbits. He wanted to come up with a purely algebraic proof, which he never did. So, but anyway. So I think this is a good place to stop. So let me stop.
Okay.
Thank you. Are there any questions?
Bob, I have a rather simple question. It's more about, since you mentioned Weinberg result a couple of times. So is it true that he classified a case where you have finite number of orbits and all they're related to this Z2 involution? Is that a case?
I'm sorry, which case?
You mentioned a couple of times Weinberg's results. So, you know, with involution.
Right.
Yeah. So is it true that he actually classified the case where there are only finite number of orbits, and they're all related to that case?
Finitely many orbit. Well, first of all, centralizers and involutions are actually spherical. So there's only finitely many orbits on G mod B in particular. But that goes back, that wasn't Weinberg. I mean, that various people looked at maybe goes back to Springer or maybe even earlier.
Mm-hmm.
In characteristic not 2 anyway. In characteristic 2, it's still true, but only by examining all the involutions and computing the centralizers and then seeing there's finitely many orbits. That is spherical on G mod B. So Weinberg really looks at the situation where you have an automorphism, semisimple automorphism on a Lie group. You decompose the Lie algebra as the direct sum of the weight spaces of this, so you get a grading on the Lie algebra. And then I think he was mostly interested in the invariant theory. So you end up showing under a suitable assumption that the ring of invariance on one of these weight spaces for the centralizer, the element acting on the weight space, the ring of invariance is a polynomial ring. By using sort of, you get sort of what's called a relative Weil group corresponding to this, and then and which is a reflection group. And so you can show that the invariants are the same as the invariance of this reduced Weil group acting on this part of the Cartan that's inside that eigenspace. So it's a very general theory and holds a much more generality than I'm talking about. But these are the cases that come up in the there's only a handful of cases that come up in looking at generic stabilizers.
Okay, thank you.
Sure.
Any other questions? So I have a question about your last slide. Could you explain a bit more what you mean by this inequality for algebraic groups?
Yeah, so is it true if it has a m orbits on d-dimensional spaces, then it has at most m orbits on d-1 dimensional spaces? So not only is it finite, but you actually have the sequence. If you look at the number of orbits, then it's decreasing as you go down.
So you replace GLV by an algebraic group?
No. I'm just saying, I'm just looking at the actions on you have some subgroup of GLV and you know it has finitely many orbits, say on the d-Grassmannian. So the theorem tells you you also have finitely many orbits on the d minus first Grassmann. But I'd like to what we don't know is that the number of orbits on the d minus first Grassmannius is at most the number of orbits on the dth Grassmannian.
Oh, I see.
Now you can also, and a related question is instead of, you can replace, I mean, that is a good question, is you can replace GLV by SO or SP and ask the same question on parabolics. Well, so so there's two, I mean, what you really want to do rather, you're not going to get this relation going in general, because for example, for D8, for SO8, all three maximal parabolics are conjugate under a triality. So you can't sort of get an inequality among them. So it's not going to be the same. But one question to ask, and I think it's been done by a recent student of Liebeck, sort of using some of our results, is classify the G contained in, say, SOV, where there are only finitely many orbits, on totally singular spaces of a certain dimension. The non-singular case, you can essentially reduce to the Grassmannian, because that's an open subvariety of the Grassmannian, the non-degenerate spaces. But you can ask for singular spaces, and I think that's been done recently. And again, there's not very many cases. But the question is the inequality. So if you go down in dimension, does the number of orbits, it can stay the same. It's pretty easy to see in some classical groups, but does that, the idea is it shouldn't be able to increase. And the proof by going via the finite groups, you don't know exactly the number of orbits for the algebraic group versus the number of orbits of the finite group. If all the stabilizers were connected, you would be fine. But if stabilizers are disconnected, then one doesn't know the exact number of orbits. I mean, if you know exactly what all the stabilizers are, you can compute the orbits. But
so you show that one is finite, then the other one is finite without actually comparing the number of orbits?
Because the point is, so I mean, what you show is that if you take G of Q, not only is it finite, I mean, obviously it's finite, but in fact, what you show is that it really doesn't, it's bounded as Q increases. So it shows you that the number of orbits of G of Q on vector space, on d-dimensional spaces over FQ is actually bounded independently of Q. And that tells you the algebraic group also has finitely many orbits. I mean, if the number of orbits was increasing, in fact, it's if and only if, in fact, of course.
Okay, and do you have these insights from finite groups, from finitely groups?
I'm sorry, do we what?
I mean, how did you discover this kind of facts? I mean, by looking first at a finite group of lead types?
No, for finite groups, it turns out, how many orbits do you have? Well, it's just the number of fixed points on the permutation module of the parabolic, the stabilizer of that. Because if you take that permutation module, it's a direct, it's a direct sum of permutation modules for the subgroup, and you get one fixed point for each orbit. So that tells you that the number of orbits is precisely the number of fixed points of the subgroup on this permutation module, and that permutation modules for parabolics, as you go up, the permutation module on, say, the dth Grassmannian, on the dth parabolic, is a direct sum of d plus 1 irreducibles. And it contains the permutation character on the d minus first parabolic, just like for the symmetric group. If you take the permutation module of Sn acting on k subsets, on the Young subgroup Sk cross Sn minus k, the permutation module of that is k plus 1, sum of k plus 1 distinct irreducibles, containing the one on k minus 1 sets. And in fact, the symmetric group result gives the result for a GL. The permutation module of GLNQ on PN of Q, on PD of Q. So it actually uses no finite group theory other than trivial character theory. So it's for any group. It doesn't use, so you're not using any deep results about finite groups. You're just using very elementary stuff.
Okay, thank you.
Sure.
There any other questions? So if not, let's thank the speaker again.